Hello everybody, let's get started for this week's discussion. So we were supposed to read through this lecture 4 and discuss any problem, issues, or any doubts that you have tonight. So is there any question from any of you on this topic or anything else?
Yes, Professor, I had two questions, I think.
Rahul? Yes.
I've listed them in the discussions. I'm just going back to the discussions to check it right now.
Yeah, let me also go to the discussion and see. So did you put it on the discussion there?
Oh, sorry, my bad. I forgot to put it. I
Okay.
made notes of it elsewhere.
Yeah, you can ask. You can ask on live on class.
All right. So I had three questions.
Mm-hmm.
The first one, so when okay, I think I've already answered, but I'll just ask you anyway. So there are two steps in there are two passes in converting the regular code into the machine, into the object code, right?
Mm-hmm.
And the two passes and reading the passes is done by the assembler, correct? Both the passes?
Yes.
Okay, neat. Okay, that covers one. The other thing, why? So, oh, so okay, I realized this also. I'm remembering from the lectures. Took me a while to digest, but then, so why don't we use macros instead of pseudo instructions? Wait, is it the pseudo instructions already written and done by the assembler itself, so that we don't need to define the pseudo
Right.
instruction?
Exactly. This is assembler provided instruction, which is not a native instruction for the processor, but as a nice gesture, assembler gives those to you so that we can write assembly program a little bit easier way than.
Okay, neat. And okay, here's the third one, and this is the one that I wasn't clear on. It's in lecture 5, part 5. You're given the example with strings. I mean, you're given an example with ASCII string, and you had written that with the my string label. Now,
right, yeah.
So yeah, okay. So where in the code is that supposed to be written? Is that writing going to be treated as a single instruction? Like, because it looked like it's written along with the other instructions.
Oh,
but then if
Rahul, which page?
yes, it's on part 5, like I mean lecture 5, part 5.
Yeah, but on your notes, can you point me to that corresponding slides or page?
Sure, I'll go to the notes right now. I'm opening the notes right now. Allow.
Is it 16, the data layout for string, that one you have question on, or?
There was no data output over there. Professor, could you share your screen? I'm not able to access it. I'm just given a message that Google tried to redirect me too many times, so I can't access the notes.
Oh, okay. Let me share. Okay. This is lecture 5 slides. All right. So we are talking about the string data layout, this one.
Yes. Okay. Yeah. This is the one.
Mhm.
So yeah. Okay. I had thought on this and I got a idea of what could be the answer to the question. But I'm just going to give you the question and the
Sure.
answer that I came up with. So you can just tell me if I'm right or wrong. Okay. So the statement uh, label part my string colon dot ASCII z the sum from 0 to 100 is that thing.
Mhm.
Initially I was thinking like this whole thing looked like one instruction line because this is going to be written with the code, right? Just as in any other line.
So basically, this is not an instruction. This is an directives. We call it a directive. That anything start with a dot is a direct
Hmm.
to the assembler, and we are
Hmm.
telling assembler that hey, lay out this string on the
Hmm.
memory, on the data memory,
Hmm.
an address which will be
Hmm.
named as my underscore string. Kind of, we put a label to that address as a my underscore string. So these don't really create any machine code. This will just place this string onto certain memory area from certain memory address, and start of that string, that address will be labeled as my str for you to refer to that address later in the assembly program.
Okay, so this is not part of the assembly program example you're given with the phase one, phase two steps. This is like a separate section of the whole assembly code.
Right. So basically, wait till the next lecture, and then we'll be discussing on the structure of the assembly program and how things are placed, what things are initialized, and so on and so forth. So hold on to this question. This is a good question, and hopefully by next lecture, this will be clear too.
All right,
Okay.
I see. I see.
All right. Anything else from anyone on the conception side? Okay.
I had another question I'd like to ask. It's not a concept question, but it's more of a what's it?
Yeah.
What class about how we're taking the class
Sure.
question. Just give me a minute. Just confirming that something. Okay, so Professor, could you describe what to expect for the next week's exam?
Next week quiz.
Yes, so is it going to be during class time or do we have a window of time in which we can take the quiz?
Uh, so basically, let me see what you can access now. It is not on yet, right? So this quiz is from. Let me see. Okay, it includes lecture 1 to 5, and it will be available from this Friday morning. Okay, and your deadline is this Saturday, which is February 20 till 11:59 p.m. 11:59 p.m. So you have this window from Friday morning till Saturday night, and it includes lecture 1 to 5. It's an open book, open note quiz. You can use your own blank scratch paper to solve the problem. You can use calculator, and you have total 45 minutes per attempt, and you have two attempts to it. Okay, so you have two attempts, 45 minutes per attempt, and setup is same as the one you did, some like a mock quiz for the initial exercises and all this stuff. Like, remember, you need to set up the webcam and that these responders lockdown browser and all this stuff, it will be the same environment that you take this quiz on. And it is open book, open note quiz. Only thing is that you need to do it yourself. Like you don't take help from others. So that's the only requirement there. And you have 2 attempts. And my best suggestion would be that you do the first attempt as early as possible, so that you know that which are the weak spot of your study, and you can go back and study them and come back and take the quiz once more. And they have the exact same set of questions in between these 2 attempts, no question variation. The purpose of that is that these quizzes are to make sure that you study and you clear your concept through this question answer session, so, and problem solving. So that's the main idea of the quizzes behind this.
That's neat. Thank you. And all right, here's the thing. So in case we are okay, so next to next week, one of these discussion classes, I might not be able to attend the complete thing. So just could you repeat what should I be doing to supplement that?
You basically go through our recordings and see if you have questions on those. Yeah.
I see. Okay. And so there are no attendance points or anything like that, right?
Not really. Not really. Yeah. If on that day, by any chance, if on that day there is a pop quiz or something, you will miss it. But again, pop quizzes are more like that 5% bonus that included in that category. So it's not of a much loss if you miss one. That's fine. Should be.
Okay. Thank you. Yeah, that clears everything I have.
Okay. All right, Rahul. So how about others? Any question from others?
Professor, regarding the quizzes, will the questions just be similar to the problem sets that you assigned?
Some, but not that difficult or that details. It is more like to judge you on the smaller points and but critical points, like more like theory oriented some problem. It is not really that complex math problem. Those are training for your midterms and other exams like final exams. Quizzes are, you can take it as a more like a subset of those problems. Like if you break down the whole problem into smaller chunk, you can expect that kind of problem in the quiz. And again, if there is a bigger problem, and let's say in the first attempt you couldn't do that, as I said, your next attempt has the same set of questions. You solve it, right, offline, and study it, solve it, and come back and give the answer to that. So it will be mix of like smaller, less hard problems and like theoretical, like multiple choice, fill in the blanks kind of problem.
I see. Thank you.
Professor?
Yes.
So I have a question similar to Rahul's. So most of the time for this meeting, I'll have to miss the last 15 minutes of it. So do we usually, I actually have never stayed past 7 in any of these meetings. So do we like, most of the time I think like when I go back and rewatch it, the like recorded sessions, you're just like continuing on the train of thought that you were kind of explaining there.
Right.
But do you, in the event of like pop quizzes or anything, would there be any in the last 15 minutes of them, or is that at the start of class?
I don't know. It really depends on the class flow and where we are. So yeah, so I cannot say upfront or cannot guarantee that there won't be any last 15 minutes. So yeah.
Okay, yeah, that makes sense. Thank you.
All right. Okay, let me first. All right. Why don't we? Why don't we do a problem set? Okay. Let's let me post that problem onto the Jamboard. I'm also sharing the screen on the Jamboard. Share. Okay. And okay. Okay, there are multiple of this problem, and I just given an imaginary system, 16-bit system with some specification, and there are 1, 2, 3, 4, 5, 6, 7 questions. Okay, so what I'll do, I'll open up the breakout room. You take about 15 minutes, maybe 6:30. We'll be back and have some discussion around that. So let's do that, and I have created the breakout room according to your study groups, so that you become more familiar with each other and stay with that group throughout the semester for your study. They are your study buddies, so you know what to do. Anyway, so let me do the breakout room for 15 minutes or so, like 6:30. We'll be back. Let's see. Okay. Option. It will be about 30 minutes, or let's say 12. Okay, open room to all. Oops, why this not? Oh, okay. Hey, are you guys assigned already? I thought I pre-assigned this.
No, I don't know if you are assigned to breakout rooms.
Ah, this is strange. I just pre-assigned them. Okay, let me do one thing. Then let me see. Andrew. 1, assigned to 1. Okay, Andrew Fang assigned to 6. And liquids assigned to 2. Okay, brand new assigned to 7. Okay, Sue assigned to 9. Okay, let's see. Kundan 5. Chekhov 1. And then Lonnie 5. Okay, Jan 6. Home. Grewal assigned to 2. 23. Okay. Okay, so let's get started and see. There's a couple of seconds for others to come back. Okay, we have all the participants. So let me see. How about that study group 6? Tony Feng, James Jian, and Dominic Reed. Do you want to share your answers and explanation on this problem?
Who did you say?
Study group 6, Andrew, Fang,
Oh, okay.
Ian, and Reed.
For A, which is
Mhm.
how many bits needed for the opcode field, we got 4 bits
Okay, why?
because it's 16 opcodes and you can express 16 using 4 bits. So you don't need any more than that.
Okay, all right. So you any specific mathematical operation you did on that 16, number 16?
Let's see, 16.
So why do you think you need 4? How do you come to that conclusion?
Oh, because 16 log base 216 is equal to 4, so it's 2 to the power of 4.
Right, exactly. Log base 2 of 16. You need to do the log base 16 of that, and that becomes 4-bit. Okay, all right. How about the next one?
How many bits for the register field?
Mm-hmm.
It was we did something similar. We took log base 2 of 8
Okay.
and we got 3 bits, and so you can express 8 registers within 3 bits.
Okay, so your explanation is that since there is 8 registers, you need to address them. You need like log base 2 of 8, that is 3 bits for them. So that's why those fields are of the 3 bits. Okay, all right. How about the next one?
The immediate field bit width.
Mhm.
So since we know how many bits opcode needs and how many bits the register needs,
Mhm.
we take 16 minus 4 minus 3 minus 3, which leaves us with 6. And
Okay.
so we said that the immediate field bit width is 6 bits.
Okay, all right. Seems okay. How about D?
D, we were working on that when we got called back. We weren't sure if we needed to express negatives or not.
Yeah, immediate is how about you give both? That's a good question, good point. Whether yeah, it is a negative or not. So if it is a negative, then what?
If it's a negative,
Mhm.
it doesn't say it's 2's complement. So I assume that it means the one before, I forgot what it's called, where it's a negative if there's a 1 at the end.
Mhm.
So that means it can.
Actually, by default, if nothing is specified, we assume 2's complement because that's the way any modern computer works. Like the other format is not used at all.
Okay.
So we always assume it's a 2's complement. So basically, if it is a range, the immediate field can have like that many bits, like here in this case 6 bits. They can represent either the unsigned values or the signed values, depending on what instruction you are actually operating on. Like there are some, we'll see of like 2-3 class down the line, there are certain set of instruction which actually operates on the signed value. For those instructions, those number of bits represent as 2's complement signed values. And there are certain set of instruction which actually takes the unsigned value from that immediate field. So for those set of instructions, those number of bits actually represent the unsigned value. So in this question, you need to actually give both the answer. Signed value range, assuming 2's complement, and unsigned value range.
Okay.
Okay, so signed value range would be that you use that minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1, which in this case it will become minus 32 to 31. And in case of your unsigned expression, unsigned value range, it will become like 0 to 2 to the power n minus 1. In this case, it will become 0 to 2 to the power 6 minus 1, which is 0 to 63. 0 to 63 for the unsigned value range. Okay.
Oh, Professor, can I ask a quick question?
Yes, Chirag.
Yeah, so for that problem, right? So 6 bits that we worked out for the immediate. So if we assume it's 2's complement, so you have negative 2 to the power of 6, or sorry, no, negative 2. You use the negative 2 to the power of n minus 1 for, and then all the way till for the range to 2 to the power of n minus 1 minus 1, right? Okay, so in that case, if it's an immediate, would there ever be any like use of having an immediate of just 0?
I didn't get your question. Immediate of 0 means what?
Like, so say the number you're representing, like in decimal, is just 0, right? So in your code, the machine code would just be like all zeros for all the whatever amount of bits, like
Right.
16 for the 32-bit MIPS. So would there ever be is there any meaning of having an immediate value of 0? Like you performed add-I or something, and you use the 2 registers and
Oh, the usage of the value 0 in the immediate field. There are some, especially with respect to the memory access. You'll see, I think, 5 lecture down the line. There are usage when we use some register value as the base address, and we want to access exactly that address without adding any offset to that address. In that case, we use the immediate 0 as an operand there. So it has usage.
Okay, thank you. Yeah, I was just wondering like why it kind of exists. Like,
That's a good question. That's a good question. There are certain usage that we need to have a 0 operand there.
okay, thank you.
Okay, now SG6. How about the FNG? So you didn't go through that, right?
Yeah, no.
Okay. All right. How about SG9, study group 9? Study group 9 is, who are study group 9? Jiang Nguyen Su, Chengwei Jiang, Wenlan Nguyen, and Qianhui Su. Any one of you wants to just come forward and share your solutions if you have reached, or you are still working on that?
Sorry, we didn't get that far.
Okay, all right. Is there anyone who actually went through F and G, E, F, G?
I've done F. I'm working on G right now.
Okay, all right. So do you want to share the F, Rahul?
Sure, I'll do F. Okay, so we have to convert jump.
Oh, you can share the screen. I just turned that on if you need to. Sharing.
Oh, I had been doing this on my
Okay.
paper, pen paper. So I'll just describe this.
Sure.
So jump 0xA6 is the code that is the thing we need to convert to machine code. Basically, we need to convert this to binary, correct?
Right.
That's yes. Okay, so and the 0x just signifies that A6 is a hexadecimal number.
Right. Right.
All right, neat. And the other thing that was mentioned here is OP code is 0xC. That means that's referring to the jump, right?
Right.
Okay. And wait, just before proceeding, when you're reading this jump 0xA6, how is it read? 0x, is it just read as 0x
So
or
this is
hex?
hex A6.
Okay, so it's just called hex while reading the hex A6.
Yeah, 0x. Anything following the 0x is the hex code. That's what it means.
Okay, so using the info from the square brackets, we can first write in the hex form that this instruction will be written as hex CA6. This will be 3 hexadecimal digits. That's only 8 bits, but we have 16-bit system, 16-bit instructions. So we can just add in an extra 0 to get the 4 extra bits to keep in mind later on. Now, so our instruction code is CA6. This needs to be converted to binary form. To convert hexadecimal to binary, we just convert each individual hexadecimal digit into binary and put them together again, and we have the binary equivalent. So C is 9, ABC3, 9 plus 3 is 12. So in binary, 12 is going to be 1100. A is going to be 1010, and 6 is 0110. Putting them together, including the first 4 zeros, which we add in zest because then the whole number is not long enough. The whole number effectively is 4 times 0, 1100, 1010, 0110.
Okay. So you have done right approach, but there
So
is
where's my mistake?
a little bit of mistake. I'll explain that. Okay. Before I explain it, why don't we just take a break? 5 minutes, then we'll be back. Like it's already 6:46, 47. We'll be back and we'll discuss more. Okay.
Okay.
All right, let's get back and let's do pop quiz tonight before we go into those two other discussions. So here, what we'll do, we will, you go to the canvas and see you have the pop quiz number 1 there. And I am going to share a poll. It is saying that, are you ready to enter the quiz password? So you basically, if you hit on the take quiz, it will ask you for the password, wait there and come back here, say, yes, you are ready. So once everyone is ready, then I will share the passcode through another poll. All right. So go to your canvas, look at that, and I'm launching the poll. And let's see if everyone is ready before I share the passcode. Okay, 11, 12 of 18 said yes. 13, 14, yes. 15 of 18, you said yes. 3 more, 16 of 18, 17 of 18, 18 more 18. Okay, all right. So everyone is ready to enter the passcode. Now, let me share another poll with the passcode. Here you go. Okay, I think all are done with the pop quiz. I will, after the class, maybe in tonight, like not immediately after the class, I'll open up the answers for you. So please look at that and see if you have any doubts or any queries, just send me an email to me on those, okay? Um, as a quiz statistics, let me just look at the quiz statistics, what happens, and maybe I can share that with you guys. Okay, share. Okay, so we have average score about 70%, high score with the 90%, 99%, and low score 30%. Standard deviation is 0.86, average time 9 minutes 12 seconds. Okay, this is not bad, not very good either. This 17% of average score. Let's make sure we actually do better in the next time if pop quiz comes up around that. Okay. Now back to our original discussion. I just updated the Jamboard with the answer for till A to E, and let's discuss about the other two problems. So here, what is going on is this. Let's say. So we are trying to convert the jump instruction, right? This one. So we are trying to do this guy. So remember from the E, what we already got, your address bit field is 12 bit. And the opcode field is 4 bit, right? So for this guy, you have this format. So this is your opcode, which is like 4 bits. And this is your address, which is the 12 bits. Now in this code, your jump opcode is given C, hex C. Anything 0x is saying that following this number is in the hex format. So that's it. So C is, as Rahul mentioned, C is 1, 1, 0, 0. That is 4 bit if you expand the C into 4 bit. And that's what will go into the opcode field. And the jump address is A6, which is like A is 1010 and 6 is 0110. But you see, like we need to fill out 12 bit, and this is like 8 bit. Now, how to do that? We'll basically prepend 4 zeros onto this. So basically what I'm saying, this guy is same as hex A0, A6. So we cannot, Rahul, especially to you, we cannot actually just like take this 8-bit and this together make the machine code. We need to follow the format. We need to fill it out 0110, 0101, and then rest of the 4-bit becomes 00, and this becomes 100, and that is your machine code. And in a hex format, if I want to get it in the hex format, then it becomes like this is C0A6. Rahul, makes sense?
That makes sense.
Okay, all right. For others,
Present.
question, yes.
Yeah, I have a question right now. So just notice something. The R colon, I colon, J colon, are they just labels?
This is like I'm saying, this is like a format type, right? We have these 3 type of instruction, R, J, and I. So this is a format for R type. The other is the format for I, and these are the J. This is not an assembly code. I'm just doing giving you the specification of of the of this assembly language for this problem.
Okay, I see. I see. I misunderstood those R colon, I colon, and J colon to be part of the instruction.
Oh, no, this is
Mistake in the previous questions because of that. I noticed that now. Got it.
So it is given there. The instruction machine code formats are the following. So these are the formats. All right. Now the next problem is a little bit trickier one. So we see that in this problem, we have 16 opcode, right? So one can think, hey, then we can actually have 16 instruction. It's not true. For the R type, you see R type has this 4-bit of opcode and then followed by this register, which is 3-bit each. And then it's the other function code field is how much? Like this 4 plus 9, which is like 12, 13. This is 3 bits, right? This is a function code field. So let me see, 6, 6, 6, 12 plus 4, 16. Yeah. So that means for R type, see the R type has the operation or function code. So this is also like function. Sometimes we call it operation code, sometimes we call opfunction code. So this R type has the function code, and note that all the R type opcode, R type instruction opcodes are always like 0. Okay, like it's like a general convention. In the MIPS, you'll see this real assembly programming. You'll see if you look at all the R type instructions opcode, you'll find it is all zeros. They are not different from each other. Only they are different from each other on their function code. So that means R type, number of R type instructions equal to 2 to the power 3, right? There are 3 bits, so 8. So number of non-R type, that means I type and J type, for them, they are distinguished from each other with respect to the opcode. Like this is my J type and my I type like this, right? Opcode and R1, R2 and immediate field. This is immediate, this is this is RS and this is RT and this is your opcode. So for I type and J type, they are distinguished with each other with respect to the opcode. They have completely different opcode from each other. So that means non-R type instructions are like with a 4-bit total, we can make like 2 to the power 4, right? But we need to exclude this 0, 0, right? This is for the R type instructions. So -1. So that becomes 8, 16, 15. So that means total number of instruction equal to 15 plus 8, which is 23. So that's the final answer for the problem G. Question?
So for non-R type instructions, the reason why it's 2 to the 4th minus 1 is because one instruction is taken up by the R type.
Yes. Okay. The one opcode 0, 0 is already taken.
Oh, so yeah. Okay.
All right. Now let's see what is our next in line. Next day we are supposed to we're starting a new module. No, not a new module. I'm sorry. It is lecture 6, which is SPEEM simulator. So we are basically starting and hands-on on the assembly programming in the next topic. Let me share that with you, and I'll show you what are the things to look for in that. Share screen. Oh, share. Okay. So we are still on module 2. So this is our lecture 6 that you're supposed to review before coming to the next class. It has about 5 different videos with some hands-on experiment along with that. And we'll start next day. We'll also start giving the programming assignment, real programming assignment. We'll start very easy, like initial like 4, 5, 6 assignments, not 4, 5, 6, maybe 3, 4 assignments, programming assignments are really easy. Like you probably need to spend 30 minutes max on top of each other. Like, and then this programming hardness will go up in an exponential curve. So please watch out for that. And as it progresses, it will go harder, harder, and harder. And so that it's kind of prepare you for the project which will be starting on after the midterm. So please ramp up on the assembly programming, but start with easy so that you get familiarized with the environment, and then we take harder problem onto us. Now here, what you need to do, you basically need to install this tool Mars IDE. Just search in the Google that for Mars SPEEM MIPS simulator. It's from, I think, Colorado University, most probably, as far as I remember. So please download that tool. It is Java. It is a Java JR file, jar file. So it should platform is not a problem. You can run it on any system. So please download Mars IDE for the MIPS or SPEEM simulator, they call it, and then explore. So basically, we talked about little bit about the simulator. What is this in general? And then we talked about system calls. This is to make like how we can print something out. Like any programming class, you start with a hello world program. Like how do you print an hello world on terminal? Or another little bit complicated program, how do you ask an input from the user? That user need to type in some numbers or a string or name, and how do you do that? Those are used by the system calls. So we'll talk about that, and we'll go with some simple program. And also, in the same experiment, we'll do some experimental macro usage. So you can be familiarized with the macro writing and how to use them in your program. So we talked about the Mars IDE, integrated development environment, and how to use them. Then we write a simple program that will print the answer is equals 5. So there are some objectives there. So we basically go through the system calls and how to use them, explanation of the code, and what does it mean. Then do the same program using some print int and print str macro. So basically we'll talk about that one, how to write it, or what next, and then we will try that out, and we'll basically then separate out the source code from the macro code and include the macro code in the original program source code and try that out. So that is another experiment, and there it goes. So basically what I want you to do is get familiarized with this Mars IDE, with this sample program, and explore that how do you use it, how do you assemble it, how do you execute the program, where to look for, what to look for, etc. Okay, just get that practical hands-on with you, and we'll take more question and discussion next day then.
All right, thank you, Professor.
All right. Good night, everybody, and see you on next